everybody. I'm going to do some definitions, diagrams, and one final T final. Okay, so Molteno says steam burns cause more damage than hot water burns. Okay, so let's look at a cooling curve. If steam hits you, okay, steam's at a high temperature, and then it condenses, it loses the heat of being a gas and the heat of the gas turning into a liquid. So you have the heat of the phase change, and heat of being at a high heat of steam, both going into your skin. So Molteno knows his stuff. He's saying a steam burn has more heat in it because it's been turned into a gas. So ouch, that's going to hurt. All right, thanks, Molteno. All right, why is this line always longer than that line? Okay, because if you want to turn a liquid into a gas, you have to get this much separation between molecules, right? And that takes a lot of energy. So it's going to take a lot of energy to make a vapor, right? If you want to turn this into this, you just have to get a little bit of separation. So it's going to take a little bit less energy. So the phase change of a solid to liquid is going to be less energy than the phase change of a liquid to gas. Truth. All right, so what is boiling point really? Boiling point's real definition is when the vapor pressure equals atmospheric pressure. So you have to know what vapor pressure means, and we have to know what atmospheric pressure means. Okay, keep that in mind. Normal boiling point, write the definition down, is the temperature when the vapor pressure equals the atmospheric pressure of 1 atm. So now we're saying, okay, when atmospheric pressure is 1 atm, the temperature that something boils at happens when the vapor pressure is also 1 atm. So what is 1 atm? It's a unit of pressure, okay? And it means all of these things. So it doesn't have to be atms. It could be 760 torr, 760 millimeters of mercury, or 101.3 kilopascals, all mean 1 atm. So that means you can change the boiling point of stuff. If you want water to stay water at higher temperatures, if you put a high pressure above water, lots of atmospheric pressure above water, then the water has to have a higher vapor pressure to turn into a gas. All right, so that's what happens in a pressure cooker. Same thing, if you lower the pressure pushing down on a liquid like water, if you lower the pressure, so let's take away some of that pressure, right, then it takes less vapor pressure to equal out. Right, so then the boiling point can be lower. So what is atmospheric pressure anyway? Well, I don't want you to look at life anymore as empty space. I want you to look at it as molecules. All right, so here's all the gas particles. There's more gas particles near the surface of the Earth, and so atmospheric pressure is about 1 atm at sea level because all these molecules are hitting you. Those are gas molecules. There's more of them there. There's more pressure. As you go higher into the atmosphere, okay, gravity's pulling less on these, so it's less pressure. So only these molecules hit you. Only those molecules will hit you as you go up. So as you increase your altitude, the air pressure is decreasing. Okay, so what does that mean about boiling? Well, we talked about evaporation happening at the surface only. Boiling happens anywhere because what happens in evaporation is these molecules escape, surface molecules. What happens in boiling is the temperature where the atmosphere, so these are the atmosphere molecules, push down equal to the vapor pressure of the liquid pushing off the liquid, okay? And so that's when boiling can happen. So that means this molecule right here can turn into a gas. These can turn into a gas, and you can get it anywhere. Okay, boiling again. So here's the air pressure pushing down equals the pressure coming off of the liquid that has already turned into a gas. So these molecules and the air molecules are hitting the same amount of times at the same amount of pressure, okay? So if you want to boil water in an airplane, okay, well, you'd be outside the airplane. But anyway, at about 79 degrees Celsius, because the air pressure is less, so then it takes less vapor to equal that. Right? And then you can see that the boiling point of water changes as air pressure changes. Okay, so we can look at a graph and help decide things like boiling point and intermolecular forces. Okay, so notice here's the vapor pressure and here's the temperature, and these represent 3 different liquids. So at 60 degrees and one atmosphere pressure, okay, All right, let me escape that. All right, so water has about, at 60 degrees, water's vapor pressure is a little over 200 millimeters of mercury. Okay, so it's not boiling yet, unless air pressure is also 200 millimeters of mercury. But atmospheric pressure is 1 atm equals 760 millimeters of mercury. So the normal boiling point of water is right here, when the vapor pressure from the water is equal to atmospheric pressure. It's going to be 100 degrees Celsius. Okay, that means the boiling point, normal boiling point of tetrachloromethane is 76.5 degrees Celsius, and the normal boiling point of pentane is 36.1 degrees Celsius. So what does this mean? Why do these things have different boiling points at normal boiling points? Well, pentane has no intermolecular forces except for van der Waals forces. And so it's going to be able to escape from itself pretty easily, and it only needs a temperature of 36.1 to have the same pressure as the atmosphere at 1 atm. Okay, tetrachloromethane must have stronger forces. Water has the strongest. Okay, so be able to read these graphs and realize that if you want the normal boiling point, you have to be in when the vapor pressure equals the same pressure as the atmosphere of 1 atm. Okay, well look, it's another graph. This time the vapor pressure is in kilopascals. And so 101.3 kilopascals is equal to 1 atm. So that means ethanoic acid's normal boiling point is about 118 degrees Celsius. Water's normal boiling point is 100 degrees Celsius. Ethanol's normal boiling point is about 80 degrees Celsius. So anything's normal boiling point is when its vapor pressure coming from the liquid is equal to 1 atm. All right, there's other kinds of graphs called phase diagrams. Phase diagrams show the relationship between pressure and temperature and state of matter. Okay, so you can see that this substance is a solid at high pressure and low temperature, which makes sense because then the molecules can be packed together and they're not moving as fast because temperature is average kinetic energy and pressure is what's pushing down on them, and so they're going to be solid. If the temperature starts to go up and the pressure stays the same, then guess what's going to happen right here? It's going to melt. Solid's going to turn into liquid. So this is going to be melting along this line right here. Any temperature here, it's going to be melting and when it's that pressure. Okay. And then as the temperature goes up, molecules move faster, faster, faster. If we're holding pressure constant, then we can get to boiling. Okay? So this line represents boiling because it's a liquid to gas phase change. This line represents melting because it's solid to liquid. If you're going this way, this is condensing and freezing. What about down here? So let's call the triple point, where all three lines meet, triple point. And that's where you could have solid, liquid, and gas all in equilibrium. Okay, so if you have all three states of matter at that temperature and pressure. Okay. Over here, solid to gas, this is going to be sublimation, and then deposition, going back towards the solid without passing through the liquid. Okay, this is crazy time. Up here, it's called a critical point, and a critical point is above which, no matter what the pressure is, then the temperature is high enough to get supercritical fluid. All right, so this tells you a little bit about boiling and melting at different pressures and temperatures and what state of matter you'll have. Okay, look, it's four more phase diagrams. Right? Here's the thing about H2O. Most substances, if you look at their phase diagrams, the liquid-solid phase change is kind of slanted to the right. Water is a little odd because its liquid-solid phase change is slanted backwards to the left. Okay, that's a little bit different. And it has to do with water's density and how water packs together at different pressures and temperatures. But notice, if the pressure is 1 atmosphere, you go here, you go down, you're getting its normal boiling point. Okay, when the pressure is 1 atm, the temperature is 100 degrees Celsius. That's when the liquid to gas phase change occurs. Okay? Carbon dioxide. Notice what happens at 1 atm for carbon dioxide. What's normal for carbon dioxide is a direct change from a solid to a gas. And so that's why if you've heard of dry ice, which is solid CO2, it sublimes and turns right into a gas. So you know how they use it in the movies to be like, so here's your solid, and then it turns into a gas and it makes all kinds of fun stuff. Okay, a couple more phase changes, but notice the different things happening here along this line, and down here along this line. Okay, so just remember at high pressure and low temp, you have solid, medium pressure, medium temp liquid, high temperature and low pressure, you have gas because there's nothing pushing down. Pressure is really low, so then particles can turn into gas. All right, so we're going to do another heat problem with calorimetry. Over here we have something about the metal. All right, metal's going to be 100 degrees to start with, and it's going to go to a final temperature. It's going to decrease, and it's going to stay solid the whole time. Water, if you read the information, it's going to start at 22 degrees Celsius, and then it's going to change temperature. It's going to stay liquid the whole time. Okay, where does the metal get the heat? Where does water get the heat from the metal? So Q of the metal is going to be equal to the heat of the water because metal transfers its heat into water. What happens because of that? The temperature of the metal goes down, temperature of water goes up. So Q metal equals Q water. MC delta T of the metal is going to equal to MC delta T of the water. And so then 350 grams of metal times the specific heat of metal, calories per gram degree Celsius, times the change in temperature of the metal. So let's think about this. The metal temperature starts high and goes low to a final temperature. So I wrote it like that, high to low. The water, on the other hand, which has a specific heat of 1 calorie per gram degree Celsius, got that from the sheet. It's going to start at, we don't know, it's going to go up, its final temperature minus its 22 degrees Celsius. It's going to start low and go high. So here's the thing about temperature change. You want to look for the final temperature of each. So the final temperature of the water is going to be higher than the final temperature, than the initial temperature. Metal's going to start high and go low. Water's going to start low and go high. But Q and Q have to be equal, so this temperature change going down cannot be negative when this one's positive. So you got to make sure that it's always bigger minus smaller to keep Q's both positive. Right? So then we do the math for this. So you know, so you do that times that, and then distribute here, minus that times that, and distribute there. So we get 3745 minus 37.45. I put 101. It's actually 100. Okay. T final is going to be equal to 450 T final minus 990. Okay. And so we need to solve for T final. So I'm going to leave it there and let you do the math. And hopefully you get 27.99 degrees Celsius. So do the math and see if you get that, then you know you're doing the math right, because it's algebra. Okay? All right, just to review, make sure you know what boiling really means, and boiling is when the vapor pressure equals the atmospheric pressure. So what is normal is the temperature when vapor pressure equals 1 atmosphere. Okay, and the atmospheric pressure is also 1 atmosphere. Okay, so boiling depends on what's pushing down. So here's your atmosphere, whatever's pushing down and whatever's coming out. And when they equal each other, that's when boiling happens at the temperature. Okay, make sure you can read a vapor pressure graph, and make sure you can read let's see. That's not the best phase diagram, but we have solid, liquid, gas. Right? Remember the key idea of calorimetry. Heat loss equals heat gain. Okay. Read your book, and then see if you can figure out why I keep putting ice skaters on here. Peace out after you look at these vocab words and the objectives. and have a great day.